about 80% of the class has not attempted most of these problems, which means that one person has attempted, one person out of the class has attempted most of the questions, and the rest of the class hasn't. So, I guess what we need to do is we need to look through and look at the different kinds of questions we have going on here. In questions like this, where they're talking about mass and velocity, momentum is the thing that makes something difficult to stop. So, in other words, momentum is kind of the moving version of what's the no. It's the moving version of Newton's first law, which is inertia, right? It's kind of like that. Inertia is this tendency of things to keep doing what they're already doing. And momentum is very similar to that. Although inertia is only measured by the mass, and momentum is measured by the mass times the velocity, and it has direction and is conserved. So it's a little more involved, a little more complex, you could think of it. But it is something that has a lot of momentum is difficult to stop moving. It's also difficult to turn, although the turning of it is a different reason. It's an inertia thing. But so essentially the one that has the most momentum is going to be the most difficult to stop moving. And that's pretty straightforward. In question 2, we have this 2,900 kilogram car driving at 29 meters per second. It needs to stop in a certain amount of time. There is an equation that tells us the force times the time is equal to the change in momentum. That's the impulse. Right? If you put a 77 kilogram passenger in the car, that adds mass to it, so it increases the impulse necessary to stop it. That's the impulse equation. Simple, straightforward equation. In this one, they tell us the mass and the velocity, and then they tell us immediately afterwards it has this other velocity, this other speed, which means it got hit by a bat. And that's what they're saying, what's the magnitude of the impulse the bat put on the ball? Well, the magnitude of the impulse is the change in momentum. So we have an impulse equaling different things. The impulse is equal to change in momentum, right here, and it's also equal to force times change in time. So you can calculate it a couple of different ways.
You can also calculate momentum from the final momentum.
Yes, that's the change in momentum. So your impulse can also equal your final momentum minus your initial momentum, right? Which would be m times v final minus m times v initial. And remember that these v's have signs. They can be positive or negative, and that's what really screws people up. You have to choose a direction for your positive, and then the opposite direction is negative. So you can actually get a change in momentum that is negative.
Is it, unless it's specified in the problem that a certain direction is positive, does it matter which direction we choose is positive? We'll still get the same answer, right? Okay.
Yes. Especially since it says here the magnitude of the impulse, right?
The magnitude of the bias, it's always positive, right?
Magnitude is always positive. It's just the value, not the direction. So here's another one that's an impulse momentum problem. They tell you the impulse, and they tell you the time. Impulse, and they tell you time. You want to calculate the force. No, they want to calculate the speed. So they've told you the impulse, they've told you the time. You can solve that for the force if you want to, or you can just take the impulse and you can plug it in here and you know that its initial momentum is 0. This one, well, this one is 0. So its impulse can be equal to its final momentum. And you can calculate that, and the final momentum divided by the mass will be its final velocity. So we have the mass here of a cannon and a cannonball, and it's going to fire this cannonball 240 meters per second. Now remember, with the cannon and the cannonball, you have the cannon, which has the big mass, cannonball, which has the smaller mass. The cannonball goes one direction with some mass and some velocity of the cannonball, and the cannon goes in the other direction. We call this mass ball. This would be mass cannon and velocity cannon. And they're opposites each other, so when you add them together, they add to equal the original momentum, which was 0. The original momentum is 0, right? So momentum before equals 0, which equals the momentum after, right? So these two things have to be equal. The cannon has a big mass, so it can have a small velocity. This one has a small mass, so it can have a big velocity. And that's the whole idea. Just conservation of momentum.
We talked about that with firearms, specifically with the larger ones, so how large guns to absorb the recoil.
That's right. Better if you're shooting a powerful gun, it's better to have a heavy gun to shoot. A light gun will bounce you all over. So how about number 6? We have a 10,000 kilogram train moving at 2 meters per second, and it hits a 1,200 kilogram car at rest, and they move together afterwards. What's the velocity of the train with the added car?
That's the elastic collision, right?
No, it's an inelastic collision. And essentially what it means is that momentum is conserved. Remember, inelastic collisions are like clay balls. They stick together. They're inelastic. They're just squishy. They don't bounce back. So in the case of the train, you have this big long train that has all these cars on it, right? So it's massive. Has lots of mass. Big M. And it's going this direction at some original velocity. And its initial momentum, this is mass train, velocity initial train. Momentum of the train initially is equal to the mass of the train times the velocity initial of the train. And then it connects with this other one that's at rest. Now these are all connected together. And then this other one is at rest. It has momentum initially 0. Right? Well, when these things hit, this whole thing is going to have a final velocity. And the final momentum, which also is going to have to equal this initial momentums added together. So if we add these two momentums together, we get initial momentum of the whole thing is just the initial momentum of the train, which was moving, the car that wasn't. Doesn't add anything to that momentum. And that has to equal the velocity final of the whole train, including the new car, times the mass of the entire train to begin with, plus the mass of the new car. This little mass here. And there you have the equation. The thing you have to solve for is this guy. Not that hard. Many of these problems are pretty much the same problem. You have a momentum at the beginning, you have a momentum at the end. This is the same thing, except in this case, you have a 22 kilogram kid who's riding in a shopping cart, and it's rolling in a particular direction, then the cart jumps off, the kid jumps off of it. He jumps off of it forward because he ends up moving forward. So what is the final velocity of the shopping cart? Well, it might be backward, it might also be forward. You never know. You have to find out. Initial momentum of cart and kid together is calculable. And then when they jump off, they're separate. When he jumps off, they're separate, and they both have separate velocities, and you can calculate that. Make sure you get the signs right. The sign will tell you which way the cart is going in the end. If it's negative, it's going backwards. If it's positive, it's still going forward. Either one can happen. And now here's another example of collision. Now we have two cars colliding with each other. We have a head-on collision, and the first car's velocity ends up being negative 0.88 after the collision. After they told us collision, they both have a velocity of 2 meters per second in the positive direction. And then afterwards, one of them has a negative meters per second. We want to know the velocity. It's just conservation of momentum, right? And you can do the kinetic energies as well. Kinetic energy is conserved, but conservation of momentum is also there. So you can do it either way. I would recommend conservation of momentum. It's a lot easier. But they do ask you to calculate the energy lost in the collision. So that's fine too.
This was one that I struggled on.
So remember that force times time is equal to impulse, right? Mm-hmm. In a graph that has force on one axis and time on the other axis, the area under the curve is going to be your impulse, because force times time gives you that area if it's a rectangle. If it's a triangle, it's a little more complicated. You have to do some calculus. Unless it's a nice triangle like this, where it starts at 3 and ends on 13, and it jumps up, looks like 1, 2 it goes from 3 to 13 in 5 seconds, so it jumps up 2 newtons every second, right? So you know the slope. So you can calculate these. You can calculate these areas under here. This, of course, this part of the area is just a square. So it's 3 by 3, or 3 by 1, sorry, which is going to be 3 Newton seconds of impulse. And if you're going from one particular one to another, you just need to calculate the rectangle down here area, and then add to it the triangle up here. Remember, triangle is height times base times 1/2. So there you go. And then, to calculate the final velocity on the object, you can use the impulse equals the change in momentum again. Because the change in momentum will tell you the change in velocity as well. Because it's mass times velocity. So they're pretty much the same question over and over again in different situations. Either you're calculating the beginning momentum and the end momentum and making them equal to each other, or you're calculating the change in momentum, setting it equal to the impulse, or to the force times the distance, or whatever else, and solving for something in that equation. There's really only 2 equations. You just got to sort out how they work. This is where it gets kind of crazy when you have to do it in 2 dimensions. We have these 2 problems in the next two here. So in this case, we have 2 cue balls that are going to hit each other, and one is sitting still, the other one is moving. What is their momentum in the y direction, in the up and down direction? It's 0. Right? In this direction, they're not moving at all. So their initial momentum in that direction is 0, which means their final momentum in that direction also has to equal 0.
Which means that they're going to be almost like equal to each other, but offset. Right?
Well, they should be equal and opposite. That's what they say usually. So let's set this problem up. We start off with our billiard ball here. It's coming here. It hits this one. You end up with them going off in these directions at these angles. Theta 1, theta 2. We have initial velocity, which is the initial velocity of ball 1. It's going to be our ball 1 is going to Afterwards, the cue ball continues at V1. Okay, so that's right. So this one is going to have a V1 up here, and this one's going to have a V2 down here. And that's great. Now, we set it up for X and for Y. Right? So in the X direction, we have components for the velocity. The initial VI1, right? This is VI, and this is V, they'll call this V naught 1. Whatever. This is final velocity, initial velocity. But in the X direction, we know that V01 is a known, so we put that in there, V01. This is also mass 1. This is mass 2. Mass 2 up here, or mass 1 up here. So initially, our initial momentum is m1 times v01 in the x direction. But our final momentum is a component of this vector right here. It is the adjacent component to theta 1, so it ends up being v0, or sorry, v1, not v0. Our final velocity in for ball 1 times the cosine of theta 1. And then for the y direction, we have 0 for our initial momentum, because it's not going anywhere, up and down. And that has to equal our, sorry, I forgot one thing. We have to add to this the other momentum from ball 2, right? So this also has to equal plus v2 plus cosine theta 2, because both those momentums have to add up. So there's two velocities here, the x direction velocities, or x components. One is related to theta 2, one's related to theta 1, and v1 and v2 also. So anyway. So this is our momentum equation for the x direction here. In the y direction, we have this component and this component, right? The one that's upward is going to be v1 sine theta 1 plus v2 sine theta 2 for the second one. And since we're going to measure all of our angles from the x-axis, counterclockwise will be positive, clockwise will be negative. So going down this way, we get a negative angle, and the sine of a negative angle is just the same as negative of the sine of that angle. So this ends up being v1 sine theta 1, which is a positive angle, minus v2 sine theta 2, but we took the minus sign out from the theta. We'll just put it out in front here. Or you could just plug in this actual angle as a negative angle all the way around. So from this second equation in y, we get v1 sine 1 theta, sine theta 1 equals v2 sine theta 2. This is great. Pretty simple. However, it's not very helpful for us in finding the answer because it doesn't give us anything that we, well, what do we know about this? I didn't check to see the things we know. So we do know, theta 1 is 35 degrees, and we know v1. So we do know that. So we can plug those numbers, v1 and theta 1, into this equation.
Wouldn't we know theta 2 since the balls after they collide, they have to be at a 90-degree angle from each other, right?
We talked about that, but we haven't figured that out yet, so we can't use that in our calculation. So, anyway, we know this angle, we know this velocity, which means we're going to be able to figure out what this has to be equal to in the end. But we go to this other equation and we can figure out something else. Because we know v1 theta 1 over here as well, and we know mass 1, oh, and these ones also have their masses. I forgot to put their masses on them, sorry. This has to be, you have to put a mass 1 here, mass 2 here, mass 1. I'm going to assume that all these masses are the same though. since they're all billiard balls?
They are, I think.
Turns out not all billiard balls are exactly the same mass, but these all have the same masses on them, mass 1, mass 2 here. So it ends up you can cancel them off because they're the same mass, the same ball. So you do get the same equation. So it's not that big a deal to do that. But over here, I didn't put the masses in, and we need to do that here. But it turns out they cancel out as well. So we end up with the same equation. So in our x equation, we have v01, the initial velocity of the ball, times v1 cosine theta, which we know everything in that. So we can actually subtract that from both sides, which I'm going to do. Subtract the v1 cosine theta from both sides, theta 1, and let that equal to v2 cosine theta 2. The great thing is here is that now we have an equation for each one of these that includes a v2 and a theta 2 in it. So we can solve. I would solve this one for v2 and plug it into this one maybe, and then solve for theta. That's what I would do. Then once you solve for theta, you can go back and solve for v2. And it's going to be a very similar problem with the cars, except both cars are moving, I believe. Gives you a little bit more of a challenge in the car problem. They're both moving, so they both have an initial velocity, they both have an initial momentum. So you have to add, instead of just one momentum to start with on the left-hand side in x, you have one in the x, and this 0 has a momentum initially also, because one of them has a y momentum. The car here is going upward in the y direction, so it has an initial momentum. So yes, that makes it more challenging, more difficult, but it's still the same problem. Then we have ranking things from highest to massest. It's not highest to massest. Highest to lowest or lowest to highest. In mass, that's easy. Velocity, then momentum, right? These two are easy. But then you got to calculate the momentums. That's not hard to do. We have a dragster with a parachute on it. It exerts a force and exerts it for a time. That changes its momentum, right? Force times time is equal to a change in momentum. So you will be able to calculate that change in momentum, which is equal to the impulse. These two are easy again, but then you have to multiply the force times the time to get the impulse. And this is the same idea. We have a force and a time, and we'll change our momentum by multiplying this force times time. But that's not going to be changing velocity. That's changing momentum, which is mass times velocity. So we have to divide our answer by mass to get the change in velocity. Same thing here. Except in this case, they tell us the change in velocity that needs to happen. We're going from 5 meters per second down to 0. So the change in velocity is going to be negative 5 meters per second. Multiply that by the mass to get the change in momentum, and that has to equal the force times the time. It's again this equation over and over again. Force times change in time equals impulse on one side, and equals the change in momentum, which is the mass times velocity final minus mass times velocity initial on the other side. Remember, these things are vectors, so they can have direction. So is the force. So is the impulse. But it's just over and over and over again, either the impulse momentum theorem or the conservation momentum. That's all it is, over and over again. Here's the rocket that's moving forward. And it's moving forward because the gas out of it is moving backwards. The gas out the back has the same momentum as the rocket going forward. So you multiply the mass of the gas times the velocity of the gas to get the momentum of the gas, and that's equal to the momentum of this rocket. And if you divide that momentum by the mass of the rocket, you'll get the velocity of the rocket.
I was stuck on that one for just a little bit, so I wasn't sure. So in that situation, we didn't have to apply gravity. We didn't have to consider gravity for the velocity.
12,000 kilogram rocket expelled backward. No, it's not saying anything that it's not telling us that gravity is involved. So. Yeah.
So it's just assuming like it's just launching that setup.
So this is just a rocket moving forward like this.
Oh, okay, gotcha.
Right?
Sorry,
Here's the gas coming out this way. It's moving this way.
I always think our rocket's launching up.
So yeah, since they just say one's going forward, one's going backward, we can assume there's no gravity involved.
Okay.
And that's that. So you calculate the mass of the gas times the velocity of the gas, and that has to equal mass of the rocket times the velocity of the rocket. You know the mass of the rocket, you know the velocity of the gas, you know the mass of the gas. You just got to solve for the velocity of the rocket, and you're done. That's initial momentum. Well, that's not initial momentum. The initial momentum of this rocket would be 0, and the forward momentum has to equal the backward momentum in order for those two to cancel out and equal 0 in the end. So here's another great example of this. This astronaut he's lost in space. He doesn't have anything to get him back to his spaceship, but he has a brick. So he throws the brick at 29 meters per second. So in other words, this brick now has a momentum of 29 meters per second times the mass of the brick, which is 1.4 kilograms. Then the mass of the astronaut times the velocity of the astronaut has to equal that same momentum. So it's mass times velocity of brick equals mass times velocity of astronaut, and you're good to go.
Mr. Daly.
Yep.
This is the one that had the weird, 20 had the weird units on it.
Did the previous one have weird units?
No, 1990, just put in the regular unit for momentum, kilogram times meters per second.
I will get to checking that, I promise.
Okay. It's not really
It just takes a little more effort to get into the code and look at it.
Yeah. And if you don't get around to it, that's fine. I just want to make sure the program is not screwed or something.
These ones are simple questions. So this is another great one for engineers, civil engineers in particular. I'm going to find out the force that's on a car, because force is going to tell you how much damage is going to happen on the person in the car. So you can calculate this. Of course, you have a car that has an initial momentum, and its final momentum is 0, and the time that it takes to get into that final momentum is 0.3 seconds. And so from our momentum equation, our momentum impulse equation, you can plug in the final velocities, initial velocity, and the masses, plug in the time, and solve for the force. And you'll see now why do they have those big barrels when you're coming off the freeway in front of exits? You see those? See those big barrels on the freeway? You know what those are filled with? Sand or water. One of the two. And the reason is because sand and water are easily displaced by a force, but it slows the car down over a long period of time. instead of a short period of time. Over a long period of time, you have much less force on it. Short period of time, much more force. Right? So this is also why you roll with the punches, right? If you have an impulse that is going to be applied to your head, like this, and you allow that force to get you for a long time by turning your head while you're being hit, then the time gets big and the force can be small. But if you run into it or just hold your head still, then the time is going to be small and the force has to be big. Right? That's why you roll with the punches. What is your question?
I was just going to, so could something similar to that be like for professional racing where they have like the giant fences to figure out?
Yeah, they have a lot of things that they do in racing and on highways and everything else to lower the amount of force by increasing the time.
Did you by chance see the really, really big wreck in the 8500 right around Memorial Day?
No, I'm not a car racing guy.
I'm not really that big into it either. I mean, it's so exciting. They're making a left turn.
Yes.
That's a left turn. But, it was on my uncle's house in the road, but they had a gigantic wreck. And it was kind of a miracle they were going to walk away.
Yeah, they're safer and safer, but they're also going faster and faster. So, their safety things tend to get canceled out by the speed. Some of these are just plugging in numbers. Some of them require a little more thinking. This is similar to throwing the brick, right? This is the egg drop. But they're all the same kind of problem. They're all either initial momentum equals final momentum. Add up all the momentums, make sure you get directions correct. And if it's in 2 dimensions, make sure you get dimensions correct also. Or they're the change in momentum equals the force times the change in time, this impulse momentum theorem. So those two things are pretty much everything we do in this chapter. One, two. This one as well. Remember, when things stick together, you have to add their masses together and then multiply by their combined velocity to get their momentum. But that's really it. Does anybody have any particular questions? Any more particular questions or specific questions about specific problems?
Not problems, just something I was curious about how momentum would be conserved in a specific situation. But we can move on, it's all right.
Ask your question.
So like a baseball pitcher, when he's standing there with the ball before he pitches the ball, he has 0 momentum because he's standing still. So how would momentum be conserved when he pitches the ball? The ball obviously is moving and has
You have to consider all the forces involved in the situation. Have you ever pitched in baseball?
Not in years.
Okay, but you have done.
Yeah.
Okay, so consider all the forces that you exert. From your feet all the way up, what forces do you exert? The first thing you do is you push on the mound, right? That's the very first thing any pitcher does to pitch, is they push off of the kick plate, right? So they go up and they wind up and they're pushing from here forward, right?
Okay.
They're pushing the earth backward. Not very much, but they are pushing. So that force has to be considered in the conservation momentum because it's part of their pitching motion.
Okay.
So that becomes a very big system.
So the reason that, at first glance, it's like, okay, the ball is moving, the pitcher isn't. It looks like momentum isn't considered. You just have to consider the fact that the earth is big enough. It's not really going to move a whole lot of that.
Yeah, the momentum is conserved and it's observable in situations where external forces are not playing a role. But if external forces are playing a role on your system, then you have to look at a bigger picture. so that there are no external forces playing a role. And that becomes difficult. And the most interesting thing about this is not conservation momentum in crashing cars and conservation momentum in rockets. The most interesting thing about this is actually conservation momentum in atoms and in star systems. Much more interesting when you get to very big things and very small things, where the external forces are just negligible. Because, you know, when you get down to the atomic level and below that, external forces almost mean nothing. You know, when you get up into star systems, external forces almost mean nothing. Every galaxy is pretty much, it's on its own out there. Doesn't have very many external forces acting.
So does it make it, you said it's interesting, does it make it easier to observe momentum?
Well, it makes it easier to observe it, easier to observe conservation momentum, but also makes it easier to predict what's going to happen in the system. So, yeah. Number what? Mass times velocity.
Yeah, and then I divided and I got right. Then the same thing on 17 and I got wrong.
So in 17, you have to be, it's not exactly the same kind of problem in 17. And the reason for that is because in 16, they've separated the masses for you. So they've told you the mass of the rocket and the gas separately. In 17, they haven't told you that. In 17, they've told you that they've told you that the astronaut has a brick. So here's the astronaut, right? And he has a brick before this all starts. Right? And the brick has a little mass and the astronaut has a big mass. So the original momentum is the big mass plus the little mass, right? Does he have an initial velocity?
No.
Says he's floating, so we can assume he's just not moving. Okay. So I guess it would be the same thing. Oh, the other thing is, listen, so it actually would be the same. Since the original velocity is 0, you get big mass plus little mass times 0 equals big mass of the astronaut times velocity of the astronaut plus little mass of the brick times velocity of the brick, right? In this one, there is a difference in this one. In this one, they tell you backwards and forwards. So they're telling you direction, so the only thing they want here is the magnitude. So this one is just positive. This one, they tell you that the brick has a 29 meter per second velocity, which is a positive number. So your number here has to be negative. So let me just check that to make sure that I'm correct in that, but I'm pretty sure that is the case. So it's 29 times 1.4 equals divided by 115. What's that? Yeah. And it's important to remember that. It's important to remember that these things do have direction. If they tell you the direction is explicitly in the problem, forwards and backwards, then you don't have to go with negative, positive. But if they tell you explicitly positive or negative, then you have to go with positive or negative. Right? That's extremely important when dealing with momentum. All right, let's move on to chapter 9 and crank out as much as we can here in statics and torque. I'll try to crank out the whole chapter in the next hour and change. We'll see how we do though. So, what is statics, first of all? Anybody have an idea what statics means?
No, I'm not going to tell you once I look at the first chapter, the first section of the book.
I love this picture, but I love one even better. It's in my office, actually.
Study of forces and equilibrium.
Chimney Rock in, let's look at Nebraska's. Everybody seems to have a chimney rock. That's not a good one. Let's do chimney rock in PHYS, Utah. I have a great picture of Chimney Rock here, but you can see from different angles of Chimney Rock there's a lot of overhang, a lot of balancing. There's another good one out there that's the one I'm looking for. So there's a lot of these rocks out in Utah, but this one was right near a place where we used to live. And I've got a great picture of it in my...
Is that Arches National Park?
It's north of Arches.
Okay. Have you ever been there?
I have not been to Arches. Oh wait, I have been to Arches. I've not been to Bryce. I've been on the edge of Arches National Park. I've seen Rainbow Bridge. But anyway, these balancing rocks are examples of what we call static equilibrium, which means they're not accelerating anywhere, obviously, but they're also not rotating. So when you're in static equilibrium, you have the equilibrium of forces, which means that all the forces add to be zero. Here's a great one. Look at that one. But you also have all of the rotational forces equal to zero. And a rotational force is what we call a torque. And what does a rotational force mean? Well, it's pretty simple, actually. Up until now, we've taken every object that we've studied. Let's name a few of the objects we've studied. We've studied cars, right? And we've studied astronauts, people, right? And we've studied, what else have we talked about in this class? Planets, right? We've studied all kinds of things, but every one of these things, when we've talked about it, we have reduced it to a point. And we've said all the forces on this car are like acting on this point, pushing and pulling and all these things, right? We've reduced these things to a point, and we call that the free body diagram. And we did that because it makes it easy. We did it for the person, we did it for planets, we did it for cars. But is that the way things really work in the world? No, it's not. For example, when you hit your brakes on your car, what happens to the car? If you're on the outside of the car, do you notice the car doing any kind of rotation or anything when you hit the brakes? Actually, I bet you do. If you look at the wheels and you hit, while they're hitting the brakes, you'll notice that the car gets closer to the front wheels and further from the back wheels. In other words, the front of the car goes down and the back of the car goes up when you hit a brakes. Have you ever noticed that feeling? You especially notice it in a truck, a much longer car, right? The reason for this is because of forces that are not acting on the center of gravity or the center of mass of the car. They're acting at different places. They're acting in front of or behind the center of mass. And so they, instead of just stopping the car, they push the car around. They rotate it around. And this happens with a person as well. You know, when a person is, let's say that we push a person in the head right here, hit him in the face, right? If we hit a person in the face, does their whole body move backward uniformly?
No, they're going to kind of
They rotate backwards, right? They do an end up, right? If you hit them hard enough. Even planets are this way, even though planets are spherical. If you push on them off axis, if you pushed on the Earth like this, instead of just pushing the Earth along, it would actually rotate the Earth, right? And so in real life, what really happens is that forces act at different distances from the center of mass or the center of gravity of objects, and they can cause rotations. When you're dealing with statics, a static equilibrium includes an equilibrium of forces where all the forces add up to equal zero, so it's not going to go anywhere in any straight line at all. But also all of the rotational forces that are off axis are going to cancel each other out and there will be no rotation. And that's exactly what's happening with these rocks. You have gravitational forces. You have a gravitational force that's acting straight down here, straight down the middle of this rock, but you also have a rotational force acting out here, which would normally pull this rock off, wouldn't it? But you have some others that are on the backside that are balancing it out. Okay?
So, just to make sure I got it, so like you're saying the rotational force is kind of on that left overhang of rock, so that if it ever fell, it would start rotating as it fell, right?
Well, yeah, if you chopped off the back end, it would do that. Because there would be nothing to counteract that, right? There are also some connection forces within the rock that are holding it, that are forcing this rock back this way. But if any of those forces were released and this was not in equilibrium, it would fall.
What I meant was like kind of the part where the rock, like you see the part that kind of looks like a neck almost,
right
part
here.
Where it's, yeah, right in there. Like if all of a sudden chink that got cut and it started falling, it would start rotating.
It would rotate to where the most forces are causing it to rotate. And just from looking at this, I would guess that it would rotate this way.
Okay.
You never really know, but until you actually measure the forces. But the same is true of even this crazy one here. You have some forces pulling it this way, but some forces pulling this way, and these are obviously balanced. There's not much holding this right here. These are obviously well balanced. And rocks in these areas fall down all the time. As it gets off balance with these forces force pieces of these rock off all the time. We have falling rock signs everywhere now. In fact, when my kids were growing up, we'd tell them a story while we were driving of the Indians who were named Falling Rock and Running Deer and Straight Arrow. Remember those, Mike Becker?
I remember those.
All the signs on the highway were Indian names to us. Falling Rock, Running Deer, and Straight Arrow. And even Curvy Arrow. Bent Arrow, I think we call it. But anyway, the point being is that this equilibrium is what we're going to be studying now. But in order to study that, we have to study these rotating forces, which we call torques. Now in physics, we call them torques. In engineering, they call them momentums. Sorry, not momentums, moments. So if you're going into engineering, be aware that you will take another class called statics, where you will call torques moments, and they are the same thing. So, here is our condition for equilibrium that we've used so far. The total forces in both directions, in all directions, always have to add up to be zero, and then you will not get any acceleration, right? There are two kinds of equilibrium: static equilibrium, which is motionless, and dynamic equilibrium, where you have constant velocity in a straight line direction, right? Those can both be equilibrium. However, if you're going to have total equilibrium, we have to talk about forces that cause rotation or may cause rotation. So torque. Torque is a force that causes a rotation about some point, or might cause a rotation about some point. Now, you can measure, you're going to have to use a measurement to that point, or to some point. And let's figure it out. Let's talk about shutting a door. How many of you have tried to open a door for somebody from the hinge side of the door? Is it much more difficult or much easier to open the door from that side of the door? It's much more difficult. So the force that you're using to open the door is actually a torque. And that torque is dependent on the force that you apply and the distance you are from the rotation point. And if you apply a bigger torque, it makes it easier to open the door. So where are you going to apply the most torque on a door for a given force? Where they put the handle, which is the reason they put the handle there, right? One of my favorite books has this mistake made in it. The Hobbit. In the book The Hobbit, all hobbits have their handles in the center of their door, which doesn't make any sense. Although to them it's stylistic and not practical. But it doesn't make sense to have a handle in the middle of a door because you reduce your torque by almost half with the same amount of force. So it makes it almost twice as difficult to open your door. But if you put it out on that outside edge, it makes it much easier. Now here's another great example of that.
Real quick, torque is momentum that's rotational, or
What's that?
what would you say, like the definition for torque?
No, we'll get there in a second.
Okay.
So here is a door that is in my hometown. Let's see if I can find it. Not the right one. This was in the original movie Tron, the original Tron movie. This door right here is a neutron. It's a neutron shield door, 17 feet thick, I believe. And you can see here that this woman is pushing this open with her hands, which you can do if you have enough torque. This thing weighs, I don't know, 3 tons or something like that. And it's still there, actually. I believe it is. But torque is about force and distance. And the less distance you have with the same amount of force, the less torque you have. And it turns out that torque is simply enough force, perpendicular force, times distance. So the distance and the force have to be perpendicular to each other. On a door, if you're pushing perpendicularly to the door the whole time you're opening it, then you're maxing out your torque. However, if you push at an angle on the door, then only part of your force is perpendicular to the radius or the distance from the force to the door. In this case right here, for example, if you push sideways on this door, only a little tiny piece of this force is perpendicular to the R, or perpendicular to the distance where you're applying the force. And if you push 180 degrees to the distance to the center, or the center of rotation, are you going to open this door with this force at all? No, you're just going to pull on the hinge, right? So that's the extreme case. That's the extreme bad case for opening the door. This is the extreme good case for opening the door, right? And it turns out that if you do the math and do the physics, that torque ends up, we use the Greek letter tau for torque. Torque ends up equaling the distance between the point of interest. We call it the point of interest because it's not always a point of rotation. But a distance between the point of interest and the point of the force acting times the force times the sine of the angle between the R and the force, or the sine of the angle between the distance to the force and the force itself. So if you use that formula, that is the definition of torque. So here's a good example. I don't know why they use a hockey stick, but they do. Probably because it has these angles in it. But we have a hockey stick that's been nailed to the wall here. We apply a force up here, and you have this R that is between A and the force, where the nail is and where the force is applied. That's the R distance. And then the angle between the force and the R is this angle here. Now, instead of using RF sine theta, you can also just measure the distance perpendicularly from the point of interest up to the extended line of force through here. But it means the same thing. The sine of theta does that. So you don't have to do that. You can do the same thing up here, applying the force down here, but now the r and the perpendicular r are the same r. So it doesn't matter. But it's r sine theta, because, you know, sine of 90 degrees is 1. So it's rf times sine of theta will give you the torque. Now, torque is a vector. But it's what we call a pseudo-vector. We're just going to pretend it's a vector. So we want to be able to determine direction for a vector, but this is a vector that has rotation involved. How do we do rotation? Well, remember when we were doing a little bit of rotation before, we talked about clockwise, counterclockwise? We're going to do that again. Torques that would cause a counterclockwise rotation, we're going to call positive or counterclockwise torques. Torques that would cause, about the point of interest, a clockwise rotation, we're going to call negative torques or counterclockwise torques. So let's now look at counterclockwise is positive, clockwise is negative. Now, let's look at an example of static equilibrium with rotation instead of just forces. In other words, we don't want this thing to accelerate up and down, sideways, and any other way, but we also don't want it to accelerate rotationally. We don't want a rotational acceleration. We want this to be balanced. So we have two children, they're on the seesaw, and they have masses, and they have distance to the pivot. Where's our children? There they are. So R1, R2, different distances to the pivots. They have different masses, so they have different weights. There's also a force here in the middle on the pivot, so that if you were calculating the equilibrium in the y direction, you would have to add the weight of both children plus the force upward from the pivot, and they would have to add to be 0 for this thing not to fly up or down, right? But we're talking about rotational, so we're going to talk about the different torques involved. We have a torque from child 1 is R1 times omega, or times W1. W1 is the weight here, that's the force applied out here, and this is the distance from the pivot. Notice that they're at an angle of 90 degrees, so the sine of theta is equal to 1, because sine of 90 is 1. For R2, it's weight 2 times R2, and it's also a 90 degree angle, but that 90 degree angle is, can we consider that one negative? Because notice that this one over here would cause the counterclockwise, so that's going to be a positive torque. This one's going to cause the clockwise, so that one will be a negative torque. That's why they put a negative on the R2, W2. R2 weight 2 is because this torque will cause a negative rotation, or a clockwise rotation. It's really confusing to people because we use counterclockwise positive, clockwise negative, but that's just the way it is.
It's like the same as a unit circle.
What's that?
It would be the same as a unit circle, right?
Yes. And in fact, that's one of the reasons. That's kind of tied, they're tied to the same reason for that. But anyway, the torque from the pivot is equal to what? What's the torque from the pivot? Well, it's R times the torque, R times the force at the pivot. Well, what's the distance from the pivot to the pivot? 0, so it has no torque, right? Whenever you're doing a problem with torques, you choose a point of interest, and then that has to be the point of interest for every force involved. You can't switch points of interest. You can't calculate different torques to different points, because that'll screw up your calculations. You have to start with one and go with it. So we've calculated all of our torques, and we know that all of our torques have to add to be 0. Well, this torque plus this torque plus this torque equals 0 ends up with this equation. You end up with torque 1, you end up with R1 omega 1 minus R2 omega 2 plus 0 equals 0, and then you end up that these two things have to be equal to each other. So when they have to be equal to each other, you get R2 W2 equals R1 W1 because of the negative on the torque 2 in the torque 2 here. It ends up positive here, so these torques end up having to be equal in magnitude. We're not dealing with their directions anymore. We're dealing with their magnitudes. And then you plug in the m times g for the weights, m times g for the weights, you can cancel out the g's, and then you can solve for the distance to the second kid. And you know all the other numbers, and you're done. Now, does that make sense? When you've got two children of unequal weights, does the lighter one sit further than the heavier one from the pivot? On a seesaw?
Yeah.
Yes. The lighter one has to sit further away. It's like getting better leverage, right? The heavier one can sit in closer and be fine.
So if you're like trying to tighten the screw down longer, the lever you have.
That's right. It's a lever arm. There's only one machine in the whole world. It is the inclined plane, which is the lever arm. And then the second part asks for the force on the pivot. Well, the force on the pivot we can get that from adding all of the forces in the y direction, which we talked about before. You have the force on the pivot, you have the minus the weight of the two children, because those are both in the opposite direction than the force on the pivot, and then you just solve for it. The force on the pivot has to end up equaling the weight of the children. That makes sense, right? The weight of the children are the things that are pushing this thing down, plus the weight of the seesaw.
But it said that was an
Yeah, which it just is not. But that's okay. Go ahead.
So, I guess I'm getting everything else except the point of interest part. We're saying that the point of interest is like the tip of that triangle where the seesaw is resting, right?
Yeah, in that case, the point of interest was the pivot.
And since the force of the pivot is going up and the seesaw is this way, that's where we're getting the angle from? Because like in the problem...
It's not between the force of the pivot. It's not about the force of the pivot. It's about the direction, the distance to the pivot. That r vector, there's a distance to your point of interest. So let's look at it really quick on our whiteboard, and let's do that. So here's an object. It's like a freakish peanut. It looks more like a rat. But whatever it is, it's just some randomly shaped object, right? Now, if there are forces acting on this in different directions and different places, then we might want to know something about the equilibrium going on here. Okay? In order to calculate torques from these forces, to do this in x and y is not a problem at all. You just say, well, this is my x direction, this is my y direction, and then I resolve all these into their x and y components, right? Mm-hmm. And then I just add up all the x's, add up all the y's, they have to cancel out to be in equilibrium. But for torques, that's not the case. To make sure the torques are in equilibrium, we have to choose a point of interest. Now it might be right there at the center-ish of this thing, might be the center, that might be the center mass, who knows. But you could also choose it over here, it doesn't matter. You could choose it out here if you wanted to. You could choose your point of interest anywhere you want. But what the point of interest is the point where you will measure all of your distances to the forces. If this is force 1, then this would be R1, and then you would have an R1 that goes from the point of interest, actually it goes from the force to the point of interest, but it doesn't really matter. But then you measure an angle between them, and that's your theta.
And that'd be, okay. So does choosing the point of interest matter, or just as long as you're using the same point?
You use the same one for the entire problem, and besides that, it doesn't matter. Now, it often makes sense to choose a point of interest where you're already going to rotate. And one of the reasons that makes sense is because often there are forces at that point of rotation which are causing it to rotate about that point, like a nail in the board or a pivot or something, right? Because then if you choose your point of interest at that point, all of the forces will have what torque at that point? All the forces that are at that point will have a zero torque. So you eliminate a bunch of forces and a bunch of torques. Well, you eliminate a bunch of torques from your equation, which is nice because, you know, torques are a pain in the butt. But the point of interest is an arbitrary choice. You don't have to choose it at any particular point. I usually look at my problems and I choose it to be the point where I have the most forces that I don't care about, so I can turn those torques into zero torques and call it good. That's usually what happens with me. And you'll see examples of where that's helpful and handy in the homework in Chapter 9. Okay, so let's go back to where we were here. What section are we in now? Stability. So here's a great example of this. You have this man holding a toy doll. They're saying that because they don't want to think that they're holding their child like this. But I've done it. If you have all your points where there are gravitational forces pulling on you in balance, then you can be in equilibrium, right? Now, so why do people who are doing, have you guys seen people doing slacklining, for example? So this is one of my favorite guys actually back here. This guy right here is one of my favorite slackliners. There's 2,000 feet of exposure underneath him. And he is slacklining across this peak here. And why is he doing this? Why is he doing this with his arms and legs? He's adjusting those forces that gravity has on him, right? What he's doing is, when he feels himself going this way, he increases the forces this way by sticking more of his body out this way so that it's more off balance, and then he balances again. I watched this guy fall from this particular one.
Like,
He falls and he grabs the rope.
instead of saying, I would hope he didn't like fall and die.
So here's what it looks like when you're after you. So this one they've tied in. He never ties in. This guy is crazy. This guy, what is his name? This guy invented this sport of slacklining in Yosemite, and yeah, he's crazy. He's done so many crazy things. Oh, here's his name, Dean Potter. What's that? Bolts.
Well, like, you gotta pick up both sides of the
Oh, he climbs. He's also a world-class rock climber, one of the best in the world.
So he climbs both sides of the rock.
Yeah. Yeah.
I was just like, does he got like a shooter?
No, doesn't exist. No such tool. You got to be able to climb both of them, or you have to be able to access both sides. You don't necessarily have to climb them. You might be able to just hike to them. But anyway, the reason for this, the movement, is to change the amounts of forces that are causing torques on your body and rotate your body back and forth, right? Now we'll learn a little bit more about this in the next chapter as we talk about tightrope walkers, because they have to do something very different. They do something very different to walk across. Tightrope walkers have a much easier job than slackliners. So, here we have some definitions. Here we have stable equilibriums. So this is called a stable equilibrium. When you push this pencil just a little bit one way or the other, or this thing, it's going to fall back to its original point and still be sitting there. If you only push it a little bit, you know. And that's because unless you go way past the tipping point, like over here, so that its center of gravity is outside of its pivot point, it will fall back to its original point and clatter back and forth and stay there. When your weight is outside of your pivot point, outside of the normal force, then you can be balanced still. You could balance a pencil this way, not for very long, but it would be unstable because if you knock it just a little bit out, it will fall all the way out, right? So those are two types of equilibrium, stable equilibrium and unstable equilibrium. And depending on what you're trying to accomplish, you may want to have one or the other. Here's some neutral equilibriums, where the equilibrium goes with the object. Something that is round is in neutral equilibrium. You have a limited neutral equilibrium, that if you go really far, then sure, but you really have to change things. And this has a lot to do with sports, right? In sports, when human beings are standing up, we're always in some kind of equilibrium. But we're much closer to stable equilibrium when we widen our feet and we sit down lower to the ground, right? It's much harder to push over a football player who's in their three-point stance on the ground. it's much harder to fall over as a basketball player if your feet are further apart. And that's why athletes do this, is to create that stable equilibrium. If you stand straight up, you're in unstable equilibrium, someone runs into you, you fall right over, right? So that's the stable equilibrium. Chickens do the same thing when they're playing basketball. So here's a question that I got wrong on my PhD exam. I got the math right, but I didn't believe it. I should have believed the math. The math of stable and unstable equilibrium is really complicated. But I did the math right, I just didn't believe the math. And so I ended up looking for some error that was not there and ended up changing my answer. Bad information, bad math. But here is a situation of equilibrium. You have a skateboard in between two walls like this. And the question was, is this stable or unstable equilibrium? You have a guess? That's what I thought. But it's not. If you knock this just a little bit out, this way will fall down this way, this one will go up that way, and it will just stay there. Just knock it a little bit out. However, this one is stable. Can you see why? Because it'll just roll back, right? This one's not, this one is. Now, I had another question. I had a question once on an exam that asked me something like this, where it was, is it stable or unstable? And there was this long mathematical process. And I just said, it's stable. And I just didn't do the math, and I got it right. I figured I had a 50-50 chance, and I didn't have time to do the math. In fact, I didn't even say it's stable. I said, sure. And I got 100% on the problem. My professor, he didn't tell us to actually do the math. He just said, he just asked the question. So I said, sure. Pretty funny. But anyway, it was his favorite answer on that exam. So, if we're going to solve a problem with equilibrium, we need to go through some steps to make sure we get everything right. First of all, we are going to be right in a two-dimensional problem like this one here. We're going to be writing out equations. One equation for each dimension, and then one equation for rotation, one equation of torques. You have to choose a pivot point or a point of interest. You have to draw free body diagrams. You should also draw the regular diagram that shows that these forces have some distance from some center point of interest or some point of interest, in this case center of gravity. And then you should write down, and then you should start your equations. Remember, in these diagrams, you're going to have angles between forces. This force is 90 degrees to this distance, if this is your point of interest. This force is 90 degrees to this distance, but you're also going to have possible rotations. So this hand is pushing this one down this way. If this is my point of interest, what direction is this one going to rotate this bar?
The right hand?
Yep.
It's going to rotate it down.
Counterclockwise or clockwise around a point of interest? That one will be counterclockwise. What about the left hand? Clockwise. So which one's going to be negative, which one's going to be positive? Which one's going to cause it?
It's going to be positive.
This one is positive. The counterclockwise is a positive torque. Right? So when you calculate the torque with this force, you'll multiply the distance times the force times the sine of 90, which would be 1. And then you'll give it a positive direction, or a positive number. And then this one would be negative. And then what is the center of gravity's torque if you're measuring from the center of gravity? 0, right? But you could also measure it from his right hand or his left hand or the end of the pole or whatever you want. But just so it's the same for every part of the problem. So once you've got an equation, you'll get an equation of forces adding together to equal 0 for the y direction, forces in the x direction adding together to equal 0, and then the torques add together to equal 0, and those are all your conditions of equilibrium. All your forces add to 0, all of your torques add to 0. And that's what they do here. So in this case, they write it a little bit differently. They write that the net counterclockwise torque has to equal negative of the net, sorry, the net clockwise torque has to equal the negative of the net counterclockwise torque, right? So all the torques that make it go one way have to equal all the torques going the other way, so they cancel each other out. Okay, that's fine. So that's our equation that we need to do. And it turns out that it's, in this case, they're using the left hand, it looks like. Yeah, they're using the left hand as their center, their point of interest. So they have a torque from the weight of the bar and a torque from the right hand in opposite directions, and they have to equal each other. So in the end, they get this equation, which is going to tell them the force from the right hand. Right? The force from the right hand ends up being 32.7 newtons with the distances. The signs of the angles are signs of 90, so they're just equal to 1. And then in the y direction, you have this equation: the left hand plus the right hand minus the weight of the pole. The right hand has a value that we know, it's 32.7 newtons. This is a value with a direction. It knows that the right hand is up. No, the right hand is down. Why did it say that? No, so they didn't get the signs correct, the signs there. But let's see here. Oh, when they subtract it over here, they get it right, so that's fine. Anyway, they get the force from the left hand is the only thing they don't know, and they solve that from the force. And of course, in the x direction, there are no forces in this case, right? So you're good to go. Torques, torques, torques. So, what is the method for going through these? First, determine whether or not the system is in static equilibrium. Make sure it's not accelerating or rotating in any way. And then draw the free body diagram. Also draw a regular diagram so you can see distances to forces. You'll need that, distances and angles to forces. And then the sum of the forces in every direction has to equal 0. So that might mean you have one equation for just x or just y. And it might mean you might have one equation for each, for x and y. And then the net torque, or the sum of the torques have to equal 0. Remember, counterclockwise being positive, clockwise is negative. Then you solve those equations and you're done. So, machines. Machines are things that are made from inclined planes. And they take advantage of that by taking advantage of torques, this idea of torque. Advantage is called mechanical advantage. Mechanical advantage is defined as the output force divided by the input force. How much force you put in is Fi, how much force you get out is Fo. And here's a great example. The lever, right? A nail puller. So you have this pivot point right down here next to the nail, and a very short distance between that and the nail. And then you have the point where you push down on it with your arm, which is very far from the pivot point. And let's do some calculations. Now, as long as we rotate this lever at a constant rotation and not an accelerating rotation, then we're still in equilibrium. We're not in static equilibrium. We're still in equilibrium. Or if we just apply a force without it rotating, so you're just applying a force to the nail and you're not actually pulling the nail out, you're just applying that force, we can still calculate the force that is applied, or the forces that are coming out of this machine. So in this particular example, well, when you do this, you're going to get a force that is applied up here, force in, a force that's applied on the nail, force out. And notice that they're in opposite directions. One's going down, one's coming up. But There's another force involved, which is the force that the nail is pushing down on the lever with, pushing down here. Then you have the normal force, which is your pivot point area. But you have this super long R here and this super short R over here. And in the end, you can set this up so that the total torques are 0 if it's not moving. That means the torque from the input has to equal the torque from the output. And this normal force is not going to apply a torque because it's going to be at the 0 point, right? So the torque on the input is the distance to the hand pushing times the force from the hand. And then that's equal to the distance to the nail times the force on the nail. Now, why are these both positive? Well, here's your pivot point. This one is going to cause clockwise rotation or counterclockwise, and this one's also going to cause clockwise, counterclockwise rotation. So they're both positive in that case, right? Now, we go ahead and solve this. Oh, actually, that is the mechanical advantage. But if we wanted to solve this for this equation for the output force, then we would flip it over on both sides. Let me see if I can do this really quick. So here's our lever. Here's our force on the, this is the force out here. This is the force in. Here's the R in, the distance. It's a much bigger, and this is a very small distance for R out. Right? This is force out. And the equation that we end up getting is that force out over force in equals R in, whoops, over R out. Right? Well, let's assume that we're going to just apply a small force on our force in. Let's multiply both sides by force in here. Let's assume that we're going to apply a small force on with our hand over here. And let's see what we get. We get big number R in over little number R out. What happens when you put a big number over a little number? You get a big number, right? So this ends up being a big number. Force out ends up being really big. And the longer that lever arm gets, the bigger it gets, right? So that's the idea behind every simple machine, from the lever arm or the ramp to the wheel. All machines take advantage of that.
Wasn't there a famous, I can't remember who it was, but give me a lever big enough and I shall move the world.
Yes. That was Greek. I have it here somewhere actually. Archimedes, yes. Syracuse. He's Greek, Syracusean. But what I was going to show you actually is my great t-shirt idea. Where did it go? I had it here somewhere. They had a t-shirt contest for the American Society of American Association of created this great t-shirt, and I can't find it now. But one of them was a lever moving the world, moving the earth, and you were supposed to guess which picture had like 6 or 7 pictures on the shirt representing different scientists. And that one was, Archimedes was the lever moving the earth. I had one for Einstein's was gravity bending space. My favorite one though is, where is that thing? I swear it was up here somewhere. But the other one was a referee with a striped shirt going like, no, making the sign for interference. What's the sign for interference in football? It's not this one, it's,
This.
no, it's, I can't remember. But it was a referee with his striped shirt making the sign. Oh, it's this is interference, right? Is that what you just said?
Yeah.
Oh, yeah. He's making this sign right here for interference. But the really funny thing is that interference patterns are stripes of black and white. So that was my favorite one. That was for Thomas Young.
I thought it was for the doctor.
What's that?
I thought you had that one for the doctor.
No, it was for Thomas Young. He's the one that used interference patterns to determine that light was a wave.
Interference or passive interference?
This is used for interference, right?
Like when a fan jumps on the field?
No, interference of any kind. So, I think pass interference, does pass interference have its own thing now?
I think so. That's the only interference I've ever seen. Pass interference.
Yeah, pass interference is this, right? Okay. Anyway,
Yeah, it says.
technically pass interference is just a type of interference. But because you can have other kinds of interference, but in football, pass interference is the most common. So, anyway, point being is that I made a t-shirt and I can't find it. Maybe it's on this screen somewhere, on this computer somewhere. Don't think so. All right. Okay, so simple machines are just examples of these things. So you have wheelbarrows and you have shovels, and they're going to do different examples of this at different angles. Now when you get into different angles so for example, here we have the wheelbarrow. The wheelbarrow has these forces that are at different distances to different points, but the distances are at angles. See, this is not a 90-degree angle anymore. These ones are fine. These ones are 90-degree angles, but this one's not. So instead of just force times distance, it has to be the force times the distance times the angle between the force and the distance. And it's the same, and there are many situations that they go through here. They go all the way down to the idea of pulleys. But pulleys are much simpler. With pulleys, where is the distance with a pulley?
Yeah, I see from the outside to the center.
Yeah, the distance is the lever arm.
The mouse is talking to you.
I'm kidding. Anyway, the distance here is from that center of rotation to the outside edge of the pulley. And that's where you get your mechanical advantage from. Now, are you going to get a mechanical advantage with just a single pulley?
Maybe a level.
Well, remember you have to compare two, right? So where's the other one? You have to have two distances and two forces. On a regular pulley like this, you have distance here and distance here. This is where you're pulling, this is where you're lifting. And the distances are the same. So the forces are going to be the same. A single pulley doesn't really help. You'll apply the same amount of force. It may help because you can put your weight into something, but a single pulley will not help. However, multiple pulleys will, of multiple sizes. Will definitely help. And there are other reasons for this as well. When you're using multiple pulleys, let's say we're pulling here and this is the mass we're lifting. Well, we put a tension on the rope here, and then that tension is going onto this rope, to this pulley, and then on the other side up to this pulley again. And this rope here is just connected to this pulley so that it can pull as hard as it needs to. So I've now doubled my tension by having two pulleys. And if I put in 3 pulleys, I can triple my tension. So this is what's called a block and pulley system. Put it in a slightly different way so that I'm pulling up on it instead of pulling down on it. I can triple my tension as well, here. So either way. In fact, I can quadruple my tension here because my pull is also going to lift this up. So pulleys make very interesting use of these things. You don't even necessarily have to have them different sizes. You just have to have multiple ropes but as they go in and out of the pulley system.
So like a single pulley doesn't do you any good because you have the tension that you regularly have, like the tension that you're pulling on, and the tension that's caused by the weight.
Yep, it's only one use of the tension.
The more tensions you have, the easier it is,
Yep.
so to speak.
Yep. That's exactly right.
I'm assuming this last section is going to be in regards to the lab, right?
It is, but it's essentially the same kind of stuff. And this is pretty much the lab that we're going to do tomorrow or Wednesday. So we won't get into it too much here. There will be some problems in the lab and in the homework on it, but it's the same idea. You have forces, you have distances, you have points of rotation, and you have equations to solve. So you can think of this arm as your door, right? Here's your hinge on your door. Here's you pulling on the door near the hinge. How hard do you have to push or pull on a door to open it from the hinge? A lot. So you put your textbook in your hand and you hold the book and you feel how much force is in that tendon. Feel it. There's a couple 100 pounds of force and it's obvious. If you grab your tendon right here, there's a lot of force in that thing. It's super tight. It's kind of scary to imagine what happens when that thing breaks. When that thing breaks, it goes flying, springs up into here, and then they have to go fish it out. All right? Then you spend like the next 6 months or a year with your arm straight all the time while it fixes it. All right? No, your body is designed to handle that kind of stress. Can you imagine what kind of biological glue is holding that thing to your bone? You cannot replace that. If you break that, it's never going to be the same again. I think the way they replace it is they actually put a titanium screw in your arm, and then they tie this thing in. But I mean, even then, it's just nothing can replace that. The biological strength of tendons and ligaments is just insane. Tendons especially. So anyway, that's something we'll do in our lab. So we're done for today. Tomorrow, tonight I'll get I'll get the homework put up so that you can get started on it if you finish up chapter 8. And then tomorrow we'll talk about chapter 9 homework, and then Wednesday we'll do lab. Sound good? On Wednesday we will leave. Did Dee talk to you about leaving early on Wednesday?
Yeah, I'm good.
2 o'clock?
Yeah.
Okay, so he'll be coming over here at 2 o'clock, so why don't we all meet here at 2 o'clock, and we'll leave as soon as we can. I got to put together a lab kit for Cassidy for the last half of the semester, the last half of the term. What do we got left in this book here?
How far in the chapters are we going? It goes all the way down to chapter.
We'll go all the way to 17 if we can. Hopefully we'll get to 17. We might end at 16. 16 is one of the ones that you're supposed to do, that's kind of required. 17 is not necessarily required. So we've got 1, 2, 3, 4, 5, 6, 7, 8 chapters left we want to do. And how many weeks do we have left? 6, 5? Something like that. Today is the 10th. We have 1, 2, 3, 4, 5. This is the last week of it, isn't it?
I thought the last day was the last.
Oh, so we have 1, 2, 3, 4. We have 4 more weeks. We have 6 or 7. Did I say 7 or 8?
I think it was 8.
8. So we got to cover 2 a week. Yeah, count them out.
Wow, it doesn't feel like summer is over. It doesn't seem like
Goes by quickly when you're doing physics and having fun. Right? We should be able to do 10 pretty quickly next week, hopefully. Yeah, it shouldn't be that hard. Then these two we can throw together. These three I'm hoping we can throw together. So we should be okay. All right. Have a good one.
We're doing talking about that calculus physics stuff.
Yes, let's do that really quick.
Okay.
So you're both in the class now, which is good. I think you are. Let's check that just to make sure.
I hope so.
Yeah, I got an email saying that they are going to finally get you in there officially.
What site is it on again?
It's on WebAssign, but I'm checking this just to summer 2017. Okay, so calc supplement, class list. Yeah, you're both in there. Okay, good. The website that we're going to do the homework in for this one is called webassign.net.
Do we need to create accounts for that?
Yes.
It says to enter a class key is the option.
Yeah, let me get you that really quick.
Okay.
Summer. Here it is. Okay, so let's see, class settings. Class key is this number right here. First, you have to put in northplatte.mpcc, and then 0889 7852. Now you're already signed into it, I believe, Cole.
Yeah, I just found the password.
I can reset it for you if you want.
Did we create a WebAssign account yet or
What's that?
no? Did we create a WebAssign account?
No.
Okay, I just wanted to make sure I didn't know to
And the reason I'm using WebAssign and not MyOpenMath is because MyOpenMath hasn't put in the calculus versions of questions yet. I don't have time to code them myself, but this company does have them in apparently. So we can.
Can you see what my username is? I got that correct.
Yes, I can. Hold on a second.
Student ID number?
Don't need your student ID number.
Huh?
Don't worry about the student ID number.
So just create an account without that?
Yep. Okay, it's K Kleinow. Kleinow. That's your last name.
Yeah.
I'm like, I was thinking it was Cole, but your Cole starts with a C. You have your email should be Gmail, right?
Yes. I don't know why it was-
And do you want me to reset your password really quick? Or do you know it?
It's, I only got a few that I do, so.
Okay.
Just
I got like 3 different variations that I do, so.
Sure, me too.
Just-
I got it.
Yes.
Should I, it's asking about the book, should I do just a single term access or a lifetime edition?
I would do, well,
I did this course.
I-
I did this course one, and it was cheaper, and it just is for this.
how much are they charging you? 20 bucks?
It's a $33.95 for the single term and $51.90 for the lifetime.
I would just do 33. The book is free online, so.
I did the
Why is it
course
charging?
one because it,
Well, they're charging you for the homework access, is what they're charging you
That
for.
makes sense.
So Lifetime will give you access to the book and the homework online for.
Okay.
What is your question, Cole? Sorry.
So the right to comment that real quick to get the credit card that we do
Yeah, you don't need to do it for a couple weeks. Well,
Well, it's asking me to do it now.
oh yeah, because I started it on. Yeah, I started it earlier. But anyway. Okay, so what we've got to do. Let's go to our book for this class, which is slightly different.
I have just something to feel on my desk, so I can put that stuff in.
Sure.
It's asking me to do that before the letting access everything.
Yeah, that's fine. I'm going to take you to the. So for the book that we're going to use, it's going to be Physics, University Physics Volume 1. Is I think what they call it. Yeah, University Physics Volume 1.
And how do you get the old volume?
Oh, it doesn't really matter. They're not charging you for it anyway. They're charging you for the homework. But the introduction is pretty similar, although they add in some more things about vectors, I believe, in the introduction. No, they don't. And then, let's see here. Dimensional theories. Yeah, so the introduction here is pretty much the same.
I'm getting signed up for that calculus physics class right now, and before they let me do anything, to get everything set up and installed, it's asking me to file access to the homework right now. So I was wondering if we could do that real quick. Okay.
There is a section on vectors here, and they use slightly different notations in some cases. For example, right here.
Okay, can you give me the number for it, please? Or the last 8 digits? Okay, let's see what's the 3 digits that we put in. And then make sure you got everything. Your name, right? Put it under your name, right? Your name, right? And home address. Okay. It's asking for contact information. It says either some sort of phone number, you know, the home or the work phone. It also has a mobile option, but it's in the okay, and then I just put your work email on there. Well, this is just paid off, yes, which I think is fine. So it's asking me to log in to your PayPal account. What email did you use? Okay, here's what it says on. Try that. said it needed to try different carbon, part of the issue with carbon or something. Yeah. Okay. I'm ready. What was that again? Okay. Okay. And 446. Okay. 646. Just complete the purchase. And just make sure it goes through. You want me to print the receipt or no? Okay, I'll just save it to my desktop. Okay, thanks, Al. Okay, talk to you later. No, I'll let you know when we get one. Okay, sounds good. Love you, Ben. Bye. Sorry about that, Mr.
No worries.
Okay, so I just bought it, so do I just close out of the purchasing part or?
Yeah, just
Okay, so. Okay, so on like the. So I'm on like the main page, so what do we?
okay. I'm putting together a homework assignment right now, so you can take a look at it really quick. Hold on just a second.
Okay. It doesn't, I didn't do that, since I just created the account, I haven't done the chapter one yet. So
Chapter 1 is essentially the same as the one we did. It's just an
Okay.
introduction to physics and units and other things. It's nothing difficult.
Okay.
However, the second chapter is a chapter completely dedicated to vectors because we do a lot more with vectors in this class than we do in the other class. Okay. So this first chapter, chapter 2, will have quite a few questions. But they're not terrible, it's just mostly calculation. And this system is set up for you to have 7 submissions also.
Okay. Are there any questions that are like just those, kind of like on the pilot map where it has, where it's just like multiple choice options?
We might have some, but not likely. It's
Okay.
mostly going to be calculation in this class.
Okay.
But let's see, what is today?
Today is the 10th.
Okay, let's put this. Let's see. All right, so now if you go up here, this is what you should see. Go to my classes, physics, and here's an assignment, chapter 2.
God bless you.
Thank you. So if I click on chapter 2 here, it takes me to this assignment. And here you've got some questions about vectors. Now this stuff is in the book, so you can read it in the book, and it's pretty good. It's pretty good reading, actually. It's very explanatory. And you'll take you right to the chapter section you're working on. But you'll notice some things about vectors that are different in this book as you go along. One of the things is that they use these bars on either side of the vector to determine to show you magnitude. So right here they're saying that A and B are equal in length, even if they're not equal in direction, right? They talk a lot about things about vectors that we already know, and that's fine. But then they get to this point here, and it departs a little bit. Here they talk about direction of vectors and a notation for that. So D goes from point A to point D. That's what this means right here. So these little subscripts tells us tells us where they start and where they end. I believe that's correct. Anyway, but more importantly is this notation right here. When they start having vectors in 2 dimensions and they start resolving them into components, we get to this point here where they, instead of just having one component and another component and writing them separately, it's actually the next section of this, they're going to write them as a sum of 2 vectors. And they don't use it as, you know, a sub x and a sub y like this. This is the way we've done it in our book so far. You have the x component and the y component, but we've never written it like this, really, where the vector a is equal to a sub x plus the a sub y component. But it is, right? If you do the head to tail thing, the x and y component add together to be the overall vector, right? And they show that right here. You have your a sub x, and if you put your a sub y over here, tail to head here, then it would add up, and then you would go from the beginning to the end, and you would have a, right? And what makes it even more confusing when you get into this version is that they don't write them just as a sub x anymore in the x direction. They actually give each of the directions, each component, each coordinate, they give them, assign them what we call a unit vector. These unit vectors are I hat for the x direction and j hat for the y direction, and for the z direction it would be k hat. And these vectors are 1 unit long, so they're one, if you're using meters, they're 1 meter long. If you're using newtons, they're 1 Newton long, or whatever. But they're 1 unit long, so that if you multiply this unit vector by anything, it doesn't affect it, because it's just 1. But it does give it a direction. So if I have 53 newtons of force, and that's my magnitude, and I multiply it by I hat, then all of a sudden I know it's in the x direction.
Okay. Does I hat, does this designate a positive x direction?
I hat designates the positive x direction.
You can have a negative I hat.
You can have a negative I hat, which would be in the negative x direction. That is correct. And so this vector right here, which is the a sub x vector, is now designated, or is now shown as the magnitude a sub x, which is the magnitude of the coordinate in that direction, times I hat, which is a vector.
Okay.
And then when you add these together, it looks like this. Here's your ax, here's your ay, and it looks like this. The vector a equals ax magnitude times I hat plus ay magnitude times j hat. Okay? Now it seems a little goofy, but it actually is quite useful. This is the beginning of some notation that you will use for a long time, and it makes the math quite a bit easier, actually,
Okay.
in the end. But they do use that in their problems from here on out. So you can see here, they actually plug in the numbers. -4 centimeters I hat plus 2.9 centimeters j hat, right? And that is the vector. This is what we call the vector form of this equation. The vector form of this, or the component form of this vector. Or you can separate the centimeters out and write it like this. It works either way. But you know that in the x direction you're going -4, in the y direction you're going 2.9.
Okay.
So,
And just one quick clarifying question. We need to go back and do the chapter 1 stuff too as well, right?
no,
We don't?
this will be your first assignment, chapter 2.
Okay, so the fact that chapter 1 is listed as a past assignment and affected at all?
Did I put a chapter 1 assignment in there?
Yeah, it has, under the part of past assignments, it has that one, and when I tried to like look in there and see if I can answer questions.
I'll just erase that one. There's nothing in chapter 1 you need to do.
Okay.
But in these problems, you're going to use that notation to do the remainder of the problems. So in this problem, for example, when they ask you what is the d vector for this diver that goes diving around down here, you're going to write that in I hat, j hat configuration. This vector is going to be written as so let's see here. We have symbols, relations, sets, vectors right here. So there's your I and there's your j. You don't have to write the hat, but you just write the I and the j. So this one might end up being 65 meters in the I direction, plus or minus 43 meters in the j direction.
So if I were to, so do I need to go over and hit that specific symbol?
I think that if you do boldface j, it ends up being the same.
So if I did Control B.
Yeah, but I think it's easier to just do this, quite honestly. Or maybe they do want you to do j hat here.
What does that button
This gives you a hat under your value, so you can put j in there. Oops, so you can put this
do?
in.
That's just to make it square?
No, that's for hats. It's definitely for hats. So if I put in the hat box, and then I click into this box, it should let me put a J in there. So I'm not exactly sure what's going to be the correct answer there, but we'll figure that out really quick. Let's take a look at my version of this really quick. So homework, where was it? This one, chapter 2, oops. So if I go into chapter 2 here, there we go. So it looks like it's writing it as, it's putting the hat on it. So yeah. So what I would do is I would do it like this. I would do vectors, and I would do the hat, and then I would put in the J like that. So I do hat, and just hit hat, and then hit J, and we'll put it in properly, I think.
Awesome.
But that's so, yeah.
So we'll just,
And then if you want it to be just a vector, if you want to use a vector symbol, then you put in the vector and then type the name of the vector, D or whatever, right?
cool.
So,
So,
Yeah, I saw that. I'm like, isn't it the same answer in both of them? And I'm just like, wait, why is there all these symbols over here?
yeah. So anyway, you can see here that this is how they type out these vectors, right? So they find the components. This is, for the vector D here, the component has a -16, which makes sense, it's pointing left, 0.1, and a 12i, and they use the angle and the sine and the cosine to figure those things out, right? So you're resolving vectors. Now, the next part that it will be confusing to you, well, here's another part that I want to show you really quick. They give you two vectors B and A, right? -3i minus 7j, -6i minus 4j. And they say, add them together. This is easy. How do you add the I hats together? You just add -3 and -6, and that's your I hat, right? This is where it becomes really easy, right? It's like factors. It's like combining like factors, right? Or combining like terms is what they call it, right? So it's just like a polynomial. You're combining like terms, and then you're good to go. However, it becomes a little more difficult when you're multiplying. And down here, they're going to ask you to multiply this. Now, in vector multiplication, there are two kinds of multiplication. The cross product, which is shown here, A cross F, and the dot product, which is here. Okay, now vector multiplication is not commutative in any way, shape, or form. Okay? It means that A cross F is not equal to F cross A.
okay.
Okay? You cannot flip them around. You have to do them in the order that they're shown. And the cross product is not what you necessarily think it is. It has a specific definition, and the dot product has a specific definition. And not only that, but when you make a cross product of two vectors, you're going to get another vector. But when you do the dot product of two vectors, you're going to get a scalar. So that's different. That's very different. And so I've given you a problem with those there, and another problem here where you have to do backwards. They give you the dot product and the cross product. You have to figure out what one of these vectors is. And then down here you have to figure out the direction of your cross product of two vectors. Okay? Well, let's talk about the cross product first. The cross product is when you multiply two cross products together and you get another vector. You multiply two vectors together and you get another vector. The important thing about this is, well, one of the most important things about this is the direction of the vector that is the result of the cross product. So you have to look at here to see this. Go look up here to see this. To find the direction of the product vector, of the cross product of two vectors, you put your hand in the direction of the first vector in the cross product. So if we're doing A cross B, this one, then we put our hand in the direction of A, and then we turn our fingers in the direction of B. Well, I can't turn my fingers down, right? Actually, I can't turn my fingers down like this, so I have to rotate my hand until I can turn my fingers in the direction of A. And you always do this with your thumb pointing out, like this. So A cross B, and your thumb points in the direction of the product, of the vector that is the result. So the result vector here is into the board, which in this case is -x, right?
Yeah.
And that is the answer right here, -x. Now that's true of any vectors, even if they're not perpendicular to each other. If I had vector on this chart, if A was up this way and B was this way, I would still do this. I would put my hand in the direction of A, and B is down this way, so I'd have to, let's see, A and B, right? Which one is it going to be? A cross B-ish, you know, like that kind of. And then it's still on the board. What it does is the cross product always creates a vector that is perpendicular to both vectors, right? And as long as your two vectors are in this plane, it's either going to be into the border or out of the border, right? And if they're in any other plane, it's either going to be into that plane or out of that plane. And always two vectors are in a plane. So that's what you're always going to get. Well, two vectors that are collinear.
And X is simply meaning that we have like Y, Z, and X is this way, right?
Yeah,
And
because it's at an angle.
expressing it in 2 dimensions.
Yeah, that's right. It's showing us 3 dimensions. So that is how you figure out the direction of a cross product. Now, how do you figure out the direction of a dot product? You don't, because it's a scalar, right?
So it has no direction.
A dot product gives you no direction. It might give you positive or negative, but it will give you no direction. And what a dot product does is kind of different. What a cross product does is it creates this vector that is 90 degrees to the original two vectors and is related to the magnitudes and directions of those vectors. And that's fine. We'll figure out what the relationship is in a minute. But what a dot product does is quite unique. I should probably stop recording since Cassidy doesn't need to know all this. Information not everybody wants to know.